Here we're starting the last section in chapter 4, section 4.6, and we want to talk about applications of exponential growth and decay. And so in section 4.2 we had a formula for continuously compounded interest. Remember we said that P represents the initial amount, or we could call it the initial value in the account, and then A is the future value. We said E is the special number, Euler's number, equal to approximately 2.72. And then R is the interest rate, and T is the time. And so all we want to do now is generalize just a little bit to say that this formula is good for more than just money. And so in particular, exponential growth is good for describing the growth of a population, and we'll see that. It's also good for describing decay, or a decreasing population, or another example would be radioactive decay and carbon-14 dating, and we'll see that example later in the section. So at any rate, all we're saying here is that in the new formula, we're saying y is a function of t. Y is a function of time t. And k is the growth rate or it's the decay rate. And you'll know it's a growth rate if the number is positive, and a decay rate if the number is negative. Y sub 0 is the initial amount, for example, the initial population, or the initial value of whatever you're talking about. And then y is the future value, or the future amount. And so let's have a couple of examples to get a better sense of this. So in example 1, the world population in the year 2000 is 6.079 billion people, and the projected population t years later is given by this formula, this function f of t. And so you can see the initial amount, 6.079, shows up there in place of y sub 0. And you can see the number in place of k. The growth rate is 0.0126, or 1.26%. So in this model, we're assuming that the population is growing by 1.26% per year. Okay, and so based on this model, what's the world population in 2010? How would you do that? Well, 2010 is 10 years after the year 2000. So 2010 means t is equal to 10. And so we just want to evaluate the function at t equals 10. 6.079 times e to the 0.0126 times 10. And let's see. If you put that in your calculator carefully, then you should get 6.895. I've rounded to 3 decimal places. And then what are the units? 6.895 what? Well, we're talking about people, not just people, but billions of people. So 6.895 billion people would be the complete answer. Okay. In part B, we're asked, in what year will the population reach 10 billion? And so 10 billion is the future amount. So what we're going to do is we're going to set f of t, the future amount, equal to 10, and solve for t. So we'll have 10 is equal to 6.079 times e to the 0.0126t. We'll divide both sides by 6.079. And I'll leave that as an exact number. I'll go ahead and cancel the 6.079. I have e to the 0.0126t is equal to 10 over 6.079. And now I want to finish solving for t. So this is something we learned to do in the last section. We should take the natural log of both sides, and the natural log and the base e exponential cancel, and we're just left with 0.0126t is equal to the natural log of 10 divided by 6.079. And we can divide off the 0.0126 from both sides, and we'll have our answer, 6.079 divided by 0.0126. And so then we just want to put that into the calculator, and let's see. Probably I don't think I need to show you that. Maybe I should, or maybe I'll show you that on the next problem. Anyway, if you put that in the calculator, you should come out with 39.5. Now that's not the answer. Remember, the question says, in what year will the population reach 10 billion? So that would be 39.5 years after the year 2000. So that would be the year 2039. And I guess if we assume that we're starting from January 1 in the year 2000, then we're about halfway through. The 0.5 tells us we're about halfway through the year 2039. So we don't round it up. We don't call it 2040, right? Because of the way the question is worded. In what year will the population reach 10 billion? That's in the year 2039. About halfway through the year. And we're done. Okay, well, let's do one more problem here. It looks a little different, but it's similar. So in example 2, how long will it take for the money in an account that's compounded continuously at 3% interest to double? So we can use the formula y equals y sub 0 times e to the kt. And since we're asked to find how long it will take for the money to double, that means that we need to solve for time t, the time it takes to double. We know that the growth rate, or the interest rate, is 3%, so we write that as a decimal, 0.03. And then we need to know one more thing. We need to remember that the future value is going to be twice as much as the initial value. So we don't actually know what either one is, but we don't need it. And we'll see why in just a second. So what we should say is that the future value, y, is equal to twice as much as the initial value. Twice as much because we're told that we want that initial value to double. Okay, so let's go ahead and plug into the formula. Instead of writing y, I'm going to write twice as much as the initial amount. I'm going to write 2 times y sub 0 in place of y. And then on the other side, I'll just leave the y sub 0 there. And then e raised to the kt. K is 0.03, and t is the unknown quantity that we're going to solve for. And now look at this equation. We need to solve for t. The great thing is that there's a factor of y sub 0 on both sides. And so we can just divide it off, and it cancels on both sides. So the upshot is it doesn't matter how much money you start with. The time it takes to double is the same regardless. So we have e to the 0.03t is equal to 2. And then we can take the natural log of both sides, just like we did in the previous problem. And the natural log and the e cancel. And we're almost done. We'll divide both sides by 0.03, and we'll have the natural log of 2 divided by 0.03, which is 23.1049 approximately. And so the problem doesn't tell us what to round to. Let's just say about 23 years, or 23.1 years if you prefer. In the homework, be careful. Make sure that you know what the problem is telling you to round your answer off to. Okay, that should do it. We'll go on and do a couple more examples in the next video.